So it gave us some idea, but smashing this into three-dimensional space, it's totally messy. I'm going to introduce it for notation's sake. If I wanted to, I could do a vertical trace where x is equal to 0 as well. And this will give us another view of what's going on in this function. And I'm not going to trace out as many examples, but if x is equal to 0, our function is going to look something like here. F of 0y is going to be equal to, if x is 0, you just get y squared plus 2, which means that you have a parabola. When x equals 0, I'm looking at the plane that's the plane of the board, essentially, because the x sticks out. If x is equal to 0, I'm flattening down, so I have just the yz plane. And the yz plane is going to have a trace of a parabola y squared plus 2. So this is my parabola. This is my trace when x is equal to 0. Gives me f of 0 y is equal to y squared plus 2. And again, I would get a series of parabolas. Because this is a symmetric function, we can see that I would get a series of parabolas as well. Let's look at another tool for being able to explore what this three-dimensional shape would look like on our two-dimensional board. Our final tool, we just did two different vertical traces. I bet you can guess where we're going. Now we're going to do a horizontal trace. So we're going to trace out what does this function look like when our z is equal to constant values. So I'm going to set my z equal to 0. What does that mean for this function? Well, f of xy is how I'm representing my z. So I'm saying that z, which is equal to f of xy, I'm setting equal to 0, which means that x squared plus y squared plus 2 equals 0. So I need to know what x and y values can I plug into this that give me an output of 0. X squared is always going to be a positive value, because if I plug something in and square it, whether it was originally negative or positive, squaring it makes it positive. Y squared is also a positive value, so I have something positive plus something positive plus 2. It's not going to work. It means that z equals 0. There are no points. There are no xy points down at a height of z equals 0. And in some ways that sort of makes sense. When we were drawing our parabolas before, notice that the lowest parabola dipped down to the point where z was equal to 2. Let's take a look at that spot. So when z equals 0, no values for x and y. But let's try a different z value. Let's try a z value where z is equal to 2. We get the equation 2 is equal to x squared plus y squared plus 2. I subtract 2 from both sides. I get 0 is equal to x squared plus y squared. In this case, we do have a solution. The only solution to this is the point 0, 0. So this is telling me that the horizontal trace, when I set my z value exactly equal to 2, I'm slicing this to be the plane z is equal to 2. I get an x and y coordinate of 0, 0. It's sort of a boring horizontal trace. Let's do a more interesting horizontal trace. If I let z equal 3, then 3 is going to be equal to x squared plus y squared plus 2, or subtracting 2 from both sides, 1 is equal to x squared plus y squared. And recall, this is actually an equation of a circle. X squared plus y squared equals 1 is the circle of radius square root 1, or radius 1. So it means that when my z is equal to 3, I'm cutting off the graph when z is exactly equal to 3. What do I get in the xy plane? I get a circle of radius 1. So this was my horizontal trace when z was equal to 2, and my horizontal trace when z equals 3 is a circle of radius 1. I'm going to do one more for this example. Let's let z equal 4. and I see that 4 will be equal to x squared plus y squared plus 2, or 2 is equal to x squared plus y squared. Again, I get a circle. This time the circle has radius square root 2. So when my z value is 4, I have a circle with a radius that's a little bigger than it was last time. And perhaps, putting all of this information together, we can visualize what's going on with this function. So the graph of this multivariable function, we've looked at the horizontal traces, we've looked at some of the vertical traces, and we knew that it was tracing out parabolas in the xy plane. I'm sorry, it was tracing out parabolas in the zy plane. It was also tracing out parabolas in the xz plane. And if I cut each of these z-planes, I end up with circles. So all in all, this equation is giving me something that looks like a bowl. It's a parabolic bowl, where each of the bowls, if I were to slice it along the bowl, along a z-plane, where z was equal to 3, let's say, I would get a circle. And if I were to slice this bowl vertically along maybe the x equals 0 plane, it would trace out a parabola. This is one technique, one tool that we have for being able to discover what's going on with multivariable functions and being able to graph those functions. Finally, I want to introduce the idea of a contour plot. Let's say that instead of representing this graph in three-dimensional space, I think of taking a top view of it. So I'm going to take a top view and look down and project this same thing down onto the xy plane. So let's say, visually it's a little crazy, but I'm going to look straight down and see the xy plane. And what does my figure look like in that case? I'm going to use all of the horizontal traces to be able to construct my contour plot. So the first of those horizontal traces was this single point at x equals 0, y equals 0, and that happened when z was equal to 2. And then the next horizontal trace we got was when z was equal to 3, and it was the circle of radius 1. And the next horizontal trace that we did was when z was equal to 4, and that was a circle of radius square root 2. And continuing outward, we would see that as we increase our z values, our circles would actually be getting closer and closer and closer to one another as we look down from the top. Because in this parabola, the radius is increasing really quickly down here close to z equals 2. And as I get out further, the radiuses are changing slower and slower and slower as I increase my z values. So as long as I keep my z step size the same, these rings are going to get closer and closer and closer to one another. So if I wanted to represent this function, instead of doing a three-dimensional graph using traces, I could do a contour plot. And the contour plot traditionally is where I'm just looking at the horizontal traces. So where my z values are changing, and I'm looking in the xy plane at the images that are traced out. You're going to have an opportunity to explore this a little more with the technology part of this lecture. So you can look at this, and the computer does a nice job drawing these pictures, probably a better job than I draw, but I think that it's very, very useful to be able to draw these by hand. That I will sometimes give you functions that look like this, and we'll have to explore, what does this function look like? Let's plot some points, let's do some traces, let's come up with a contour plot to be able to describe it.